All right, let's think about this together. So you've got an element that's an automorphism of Z20. So that's an isomorphism from Z20 to itself. And we're assuming that it maps 5 to itself. Question is, what are the possibilities for phi of x? And it is kind of an open-ended question. It doesn't say prove those are the only possibilities. So I guess, if I assigned this as a problem where I was grading it, I'd be looking for basic reasons for the answers and give some basic reasons. And one thing that I told you to think about is the fact that generators get mapped to generators. That's because isomorphisms preserve orders. And so you have to think about that. That's one thing to think about. Another thing that's worthwhile to think about is this. The fact that phi is an automorphism, again, meaning an isomorphism from Z20 to itself, means it's operation preserving. And since the operation in Z20 is addition, that means if I have an arbitrary element x from Z20, I can think about finding phi of x by adding 1 to itself x times and applying phi to that, right? Given an arbitrary x in Z20, like say 14 or something, 14 is 1 added to itself 14 times. Since phi is operation preserving, with respect to addition here, that will give you the same thing as phi of 1 plus phi of 1 plus phi of 1, etc. Also 14 times if x were 14, and in general x times. And that, because again, the operation is addition, is the same as x times phi of 1. Right? In multiplicative notation, we think of that as phi of 1 to the x power, but the operation is addition, so we think of it as x times phi of 1, really meaning add phi of 1 to itself x times. And take a look at this. This is telling you the formula for phi of x has to be of the form x times something, something times x. Of course, mod 20. So yeah, if I know what phi of 1 is, that completely determines the formula for phi of x. I don't know if you remember from linear algebra, when you were talking about linear transformations and bases in linear algebra, you might remember that linear transformations are completely determined by how they map basis elements. You remember that? And in fact, the columns of the matrix that represents the linear transformations can be found by applying the linear transformation to the basis vectors in 3 dimensions. That's sometimes called I hat, j hat, and k hat, or E1, E2, E3 are common notations for basis vectors. Very similar kind of thing here, using the fact that it's operation preserving. If we know what phi of 1 is, we know what phi of x is. And it's got to have this kind of formula. But again, phi has to map generators to generators, so I can't just let phi of 1 be anything. It can't be 2, for example, because 2 is not a generator of Z20. Or 5. It's got to be, in fact, one of these 8 numbers. And so then the question is, which of those are also consistent with this? Well, certainly if phi of 1 is 1, that's consistent with it. Then phi of 5 would be 5 times 1, 5. Are any others consistent? Possibly. So phi of x could be x. Let's just do mental calculations here. I multiply any of these numbers times 5 and then mod by 20. Which ones give me 5? 3 times 5 is 15, mod 20 is 15. 7 times 5 is 35, mod 20 is 15, not 5. 9 times 5 is 45, mod 20 is 5. 9 is a possibility. 11 times 5 is 55, mod 20 is 15. No, that doesn't work. 13 times 5 is 65, mod 20 is 5. 13 is a possibility. $17 times 5 is what? 85? Mod 20 is 5. 17 is a possibility. And 19 times 5 is 95. Mod 20 is 15. That's not a possibility. So these are the only possibilities. And again, it's assumed mod 20. You don't really need it for that first one, but for these other ones, you would need to make sure you mod by 20 when you use the formula. So there's 4 possibilities. For an arbitrary automorphism of Z20, what else could 5 get mapped to besides itself? And as I was thinking through the examples, I was implicitly mentioning the other possibility. Or actually explicitly. What else could 5 get mapped to besides itself? When I divided by 20, I kept getting either 5 or 15. Yeah. Which makes sense if you think about the orders. 5 has order 4 in Z20, right? Because 4 times 5 is back to 0. 15 also has order 4. 4 times 15 is the first multiple of 15. That gets you back to 0 mod 20. Isomorphisms have to preserve orders. If you picked some other number that's not a generator, like what if you use the formula phi of x equals 2x? Wouldn't that still be operation preserving? Because it's still linear. 2 times x. It would still be operation preserving. The problem it would be that it would not be 1-to-1 and onto. It would not be 1-to-1 and it would also not be onto. That would be the problem. Such operation preserving functions that are not 1-to-1 and or not onto still can be important for us. And in fact, we'll see in chapter 9 that they're important. Actually, it's chapter 10. They're called homomorphisms instead of isomorphisms if they're just operation preserved. All right, let's continue thinking about that fact we were talking about at the end of class on Wednesday. The fact that G being isomorphic to G bar implies that ought G is isomorphic to ought G bar. I saw that this is actually a practice problem from chapter 6. And I hinted at what to do at the end of class on Wednesday. Let's try to see if we can be a bit more detailed in class here today. Could I see putting this on the next test? Parts of it, maybe. I think the entire proof of this fact probably is too long, too tricky. Maybe parts of it with some hints. It's certainly important enough to highlight. It's an important fact. And remember, it also means the contrapositive of this is true because anytime an implication is true, the contrapositive is always also true because they're logically equivalent. The contrapositive says if ought G is not isomorphic to ought G bar, that implies G is not isomorphic to G bar. And you might say the contrapositive is more important as far as applying this to studying groups. You got 2 groups, you're trying to tell if they're isomorphic. Maybe the groups themselves are hard to understand, hard to work with, but maybe for some reason the group of automorphisms are easier to understand. Maybe. It's hard to imagine such a situation necessarily, but maybe. It's not without the realm of possibility. And so if you could show these are not isomorphic, that would imply that these are not isomorphic. If these were isomorphic, it doesn't imply that these are isomorphic. The converse is not necessarily true. In fact, it's definitely not true. You can come up with examples. just because these are isomorphic does not mean these are isomorphic. I think, for example, U10 and U20 might be examples of that. Or I meant to say Z10 and Z20. Because I think U10 and U20 are isomorphic. And remember, Zn is isomorphic to Un. That's a theorem in the book. So what I'm saying is, if you're thinking about odd of Z10 and odd of Z12, I'm not positive, but I think those are isomorphic because they're both isomorphic they're isomorphic to U10 and U12, which are isomorphic to each other, I think, if I recall correctly. And then, but Z10 and Z12 are not isomorphic. Get what I'm saying? I said that kind of in a weird way. Should I say it again? The converse of this is false. I believe the example Z10, thinking about Z10 and Z20 or Z12 would be enough to confirm that. Because odd of Z10 is isomorphic to U10, and odd of Z12 is isomorphic to U12. And if I recall correctly, I believe both of these are isomorphic to each other. They are different groups, but they're isomorphic. They're both cyclic, I believe. Think about that. For example, is 3 a generator in U10? Yes, it is. Is 5 a generator in U12? 5 times 5 is 25. No, it's not. Is 7 a generator? No, it's not. Maybe I'm wrong. Okay. This might be the wrong example then. But there are examples like that where the U groups are going to be isomorphic and therefore the odd groups are isomorphic, but the individual Z's are not isomorphic. For example, they have different orders. Yeah, U8 is not cyclic though. U8 and U12, I bet it works. So again, these two things, if I'm remembering correctly, thinking correctly, these are not cyclic. They're both order 4. They are isomorphic, and therefore these are isomorphic. But Z8 and Z12 are not isomorphic. Anyway, coming back to thinking about proving this. How would you do it? Well, you're assuming G and G bar are isomorphic, therefore there must exist an isomorphism between them. Phi from G to G bar, that's 1-to-1 onto an operation preserving. You want to show that odd of G is isomorphic to odd of G bar. So you've got to find an isomorphism. Besides being an important fact, I think this is also worth doing because it's going to emphasize a key thing to realize when you're thinking about many problems that have kind of a similar feel here. It's not real clear what to do when you first start thinking about it. However, if you think about it long enough, you ultimately realize there's only one reasonable thing to try. And that comes up a lot, and it's going to come up a lot in the next week and after spring break. A lot of situations when we're thinking about facts in group theory, it's not clear what to do at first, but when you think about it long enough, and hard enough, you hopefully start to realize there's only one reasonable thing to try, and you just hope that that works. What do I mean? What's the only reasonable thing to try? So we want to come up with an automorphism. I'm going to find an isomorphism, call it psi, from aught G to aught G bar, which means in the first place, you need to come up with a mapping from aught G to aught G bar and hope that the mapping is an isomorphism. Does that make sense? Like what's a function from this domain to this codomain even? What's an example of such a function? We got to use this function somehow, right? That's one thing that's like an only thing we can do. One that's not the complete picture, but somehow we got to use that function. Might be helpful to draw a diagram like this. I'm going to draw G here and G bar here. Phi goes from G to G bar. I want to think about even coming up with such a function. I have to be given an automorphism of G and map it to an automorphism of G bar. What's an automorphism of G? It's an isomorphism from G to itself. Maybe I should draw something like this. What should I call it? Oh, how about alpha? Need another Greek letter. It's not a permutation. Well, actually, that's a bit of a lie. It is a permutation. Because remember, permutations are just one-to-one and onto functions from a set to itself. So actually, any automorphism is a permutation. But it's more than a permutation. It's also operation preserving. G could be an infinite group, though. Is there a way to look at this diagram and figure out how to take this alpha and this phi and create an automorphism from G bar to itself? There is, though you come at it in kind of a roundabout way, you might say. First, evidently, if I'm going to use both phi and alpha, I need to go backwards from G bar to G. How about use phi inverse? Then apply alpha, then apply phi. That will be a mapping from G bar to itself. And it's like the only possible mapping you can possibly think of. Does it make sense to say possible twice like that? The only possible mapping you can possibly think of from G bar to itself based on what I'm given. It's got to be the answer. In other words, psi of alpha, I want it to be an automorphism of G bar. It's got to be the function where you apply phi inverse first, then alpha second, then phi third. It's got to be a function composition. And with our convention of function composition going right to left, it would have to be phi alpha phi inverse. That's got to be the answer. That's got to be the isomorphism from odd G to odd G bar. I mean, I haven't proven that it's an isomorphism, but that's the only thing you could possibly think of. At least that's fairly simple. I mean, I could go more complicated. I could say, okay, I'm going to map phi inverse. Then I'm going to map alpha 7 times. Then I'm going to map phi, and then I'm going to map phi inverse. Then I'll map alpha 13 times, and then come back and map phi again. I could do something like that. And I guess that could be an isomorphism as well. I guess it would have to be, actually. But this is the simplest thing to think of. Yeah, and the fact that it's an automorphism of G bar is actually obvious. Well, at least based on things I mentioned before. When you compose one-to-one and onto functions, you get a one-to-one and onto function. It's certainly one-to-one and onto. Is it operation preserving? I guess I haven't fully proved that, but it is. You compose operation preserving functions, you're going to get an operation preserving function. If you wanted to verify it, you'd actually want to verify something like this. Psi alpha of G1 bar, G2 bar. Does that make sense? G1 bar and G2 bar are arbitrary elements of G bar. I'm trying to show this psi of alpha, which is this function, is operation preserving on G bar. That's why I'm using the bars over the G1 and the G2 to emphasize those are elements of G bar. And well, how do you do that? Well, what's the formula for psi of alpha? It's this. This is going to be phi alpha phi inverse of G1 bar G2 bar. And now just use the definition of function composition and just keep applying the fact that these functions are all operation preserving. This is phi of alpha of phi inverse of G1 bar G2 bar, lots of parentheses. Each one's important. More parentheses to come. Now use the fact that phi inverse is operation preserving to write this. Next, use the fact that alpha is operation preserving to write this. Can I fit it all on one page? Finally, use the fact that phi is operation preserving. Running out of room. Can I do it? Wow. Am I done? Yeah. Because this whole thing is the same as psi alpha of G1 bar times psi alpha of G2 bar. What fun. By the formula for psi alpha. Isn't that crazy? If you like this kind of thing, that means you like abstract math, right? Just a bunch of symbols. Show this to your parents, they're like, what are you learning at college? What good is this? Well, it's good in proving this fact and necessary to prove this fact, which is helpful for studying groups, which if you're a pure mathematician is a good enough reason in and of its own right. If you're an applied mathematician or maybe more have a scientist or engineering bent, you're like, well, what is it good for in science or engineering? Well, again, the book does have examples of applications. A lot of the examples are focused on cryptography. And if you go further into the book, there's emphasis of applications to coding theory, which is related. There's something called error correcting codes, which is important for communications, detecting errors in communications. They do mention applications to science, crystallography, studying, molecules. What structure does this molecule have, for example? How do you know? You have to use crystallographic techniques. That might not be a word. Crystallographic techniques, which do involve using some machinery to shoot lasers through different molecules or different crystal structures. And based on the pattern of those lasers, you can evidently use group theory to decide what shape the molecule has. There's a high-level application. And it is an application of group theory because, you need to know facts from group theory to be able to understand how to apply group theory to that kind of situation. So yeah, if you like this kind of thing, you're more likely to be pure mathematicians than the average person on the street, but I think even with math majors, not everybody likes this. But if you do, you kind of think it's fun, it's like, well, that means you really like pure math. You're a pure mathematician at heart. Certainly easy to get confused, certainly easy to make mistakes with all the parentheses. And I was trying to emphasize all the parentheses are really important, actually, but I could have made a mistake as well. So you got to double check things. Does that make sense? Can I clarify anything there? And again, it emphasizes the theme of, well, this is like the simplest thing to try. You just hope it works. And often it does work, at least based on the fact that these these theorems are, in a sense, kind of set up to work in the first place, in a way. What about those inner automorphisms that you read about, what we haven't talked about yet? An inner automorphism sorry about that. An inner automorphism is an automorphism, but of special kind. Of G, a group. In other words, i.e., an element of, haven't written this in class yet, but you've seen it in the book, in G, INN as an abbreviation for inner, is an automorphism of G with a special kind of formula, with a formula of the form, let's say the symbol for phi is, for the automorphism is phi. Phi of x equals a times x times a inverse for some a in G. So any function like that in that form with that formula, assuming the group operation is multiplication, is an inner automorphism, and conversely, any inner automorphism of G has this kind of formula. This is a definition of inner automorphism. Nothing to prove here, it's a definition. Well, that does bring up a question, though. Are these things with this kind of formula really automorphisms? They certainly map G to itself because you're multiplying things in G, and G is closed. And A is in G, and so would X be when you're plugging an element in for X. Is it one-to-one and onto? Is it one-to-one? One-to-one question mark? If you assumed phi of X was equal to phi of Y, does that mean X equals Y? Because you can just use cancellation. I really used both left cancellation and right cancellation. I'll just say by cancellation. All right, cancel the A's on the left and the A inverses on the right. If you want to give extra reasons for that, you could literally multiply both sides of this on the left by A inverse and on the right by A. So yes, it's one-to-one. Is it onto? Give me some Y in G. What X gets mapped to Y? Given Y in G, how should X be chosen so that phi of X equals Y? And can you always choose such an X? And that essentially is equivalent to solving this equation for X. Multiply on the left by A inverse to get this equation. And multiply both sides on the right by A to get that equation. Those implications do go both ways. So this is really enough of a proof. But if you wanted to be extra picky about it, you could say phi of A inverse YA is using the formula A times A inverse YA times A inverse. And then, yeah, by the associative property, can write this, and then you can write that like this if you want to be extra careful about it. I equals E. No, EYE equals E. That was a joke. I equals E. Oh, no, it doesn't. It equals Y. What am I saying? I equals Y. Hey, those rhyme. Just get joy out of doing this stuff. You can humor yourself in so many ways. Is it operation preserving? OP question mark. Uh-huh. What's phi of xy? That would be A times xy times A inverse. Is that the same as phi of x times phi of y? Yeah, after you do a little calculation, it is. Again, if you want to be extra picky by using the associative law here. I think we're at a point where you don't have to show all these steps. These match. We're happy. So inner automorphisms are automorphisms. I made that part of the definition, but it's not literally part of the definition. Technically speaking, it does take a proof. What are inner automorphisms good for? Well, one thing they're good for is they are nice, simple examples of automorphisms. They have a nice formula. What else would they be good for? Well, for one thing, if you think about it, if G is abelian, this formula simplifies just down to X, right? A inverse can be swapped around here, the X and the A inverse, to give you just X. In other words, if G is abelian, there's only one inner automorphism, the identity mapping every X to itself. So this is only interesting, you might say, when G is non-abelian. And you might intuitively think of it in terms of the fact that maybe the more non-abelian G is, maybe the bigger in G is, maybe. Remember, like we mentioned 15 minutes ago, odd Zn is isomorphic to Un. So, I mean, Zn is abelian. So odd Zn is non-trivial. However, in Zn, because Zn is abelian, is isomorphic to the trivial group. Just an identity element by itself. So maybe the more G is non-abelian, if that phrase makes sense, the more likely in Zn is going to be closer to what odd Z, or in G would be closer to odd G. Maybe they'd even be the same. It's possible. Maybe every automorphism is an inner automorphism for certain non-abelian groups. Maybe. Just trying to think in hypotheticals here. We are going to see applications of these ideas in some later chapters. It's mostly chapters 9 and 10 where we see application of these things. Yeah, in fact, here's an application, so to speak, right here. Now, this doesn't have any meaning to you right now when you look at it. This is in chapter 9. For any group G, G slash Z of G is isomorphic to in G. But what is G slash ZG? I haven't talked about that yet. I'll have to wait for after spring break, probably. And again, the goal is, do these things help you understand groups? Do they help you classify groups? And the answer is yes, they do. They are tools. that seemingly don't have any applications at first, but we find application to abstract group theory and the fact that they help us classify groups, especially finite groups. All right, I'd like to end class in about 10 minutes. Let's do one more thing. Let's introduce chapter 7. Chapter 7 is about the most important fact in group theory. Hey, better pay attention to chapter 7. The most important fact in group theory is called Lagrange's theorem. Here it is. We've hinted at this theorem already. If G is a finite group, I should say it's the most important theorem of finite group theory. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. So we've hinted at this before. In fact, we have talked about another theorem that says that same thing in the context of cyclic groups. And it says even more than that. The fundamental theorem of cyclic groups says if G is cyclic and H is a subgroup of G, then the order of H divides the order of G. But it says even more. It says for each divisor of the order of G, there's exactly one subgroup of that order, and tells you how to figure out what it is as well. This says G is any finite group, cyclic or not. H is a subgroup, then the order of H will divide the order of G. So looking at the divisors of the order of G gives you the possible sizes of subgroups. Not guaranteed that there will be subgroups of order equal to each divisor, but just the possibilities. It tells you what the order of subgroups cannot be. It cannot be some order that does not divide the order of G. So if the order of G is 60, for example, the only possible subgroup sizes are 1, 2, 3, 4, 5, 6, then jump to 10, divisors of 60, then 12, then 15, then 20, then 30, then 60. Of course, you always have the trivial subgroup order 1 and the entire group itself order equal to the order of the group itself. But in a group of order 60, we are, for example, not guaranteed to have a subgroup of order 30. Possible, but not guaranteed. And in fact, A5, the alternating group that has on 5 elements, even permutations, has 5 factorial over 2 elements, which is 60 elements. Actually, that group has no subgroup of order 30. Says a bit more. Moreover, the number of distinct left cosets of H and G is that. But wait, what's a left coset? And why is there a right in there as well? Okay, that's what we'll spend our last few minutes talking about is cosets. Let's think about it in the context of an example. Let's go back to D8 and its Cayley table to help us here. Back in chapter 1. There's D8. Rotation, symmetries of a square. What is a coset? Well, first of all, what is a left coset? Given a group G and a subgroup H of G, and an element A in G, the left coset of H in G containing A, that's a long term. That's say the full thing. Left coset of H in G containing A is the set denoted by AH, make A lowercase and H capital. And this is just notation that for a set that can be described as the set of all products A times little h, where little h varies over capital H. The textbook actually defines this set even when H is not a subgroup of G. However, even if H is just a subset. However, I have never bothered to think about this concept when H was not a subgroup, it was just a subset. You always think about this context where H is a subgroup. That's where it's useful. And what's it useful for? The main thing it's initially useful for, at least, is proving Lagrange's theorem. As you read chapter 7, you'll see that, based on properties of these cosets. So, for example, coming back to D8, let's take an example subgroup. Oh, how about the subgroup containing R0 and H? Subgroup of order 2. And by H there, I mean the horizontal reflection, not a subgroup. Unfortunate notation. Let me call the subgroup K. Let K, capital K, be R0, comma H, and that is a subgroup of D4. This is an example. So K is going to be my subgroup. I didn't want to use the letter H. What are the left cosets that we can make? Well, there's R0K, which would consist of the set of all products of the form R0 times something in K. R0, I should say, composed with itself, R0 composed with H, where H is the reflection about the horizontal line, symmetries of a square. Pretend this is a square. H is that reflection. And well, R0 is the identity. This just gives us H back, or K back, I should say. What if I did HK, make the H small and the K big? That would be this set. Hey, but that's also equal to K. Right? With sets, it doesn't matter what order you put the elements. These are the same sets, they've got the same elements. Or, all right, well, what about something else? What about like R90K? Take the elements of K and multiply on the left by R90. R90, R0, and R90, H, giving us a set R90, comma, what's the other one? Go to the Cayley table. R90 composed with H is what I'm after here. R90 composed with H is D prime. Not equal to K. Not even a subgroup, right? Doesn't even have the identity in it. Cosets are usually not subgroups, even when H itself is a subgroup. I don't have time to do these all. Let's do one more. How about D prime K? Set containing D prime compose R0 and D prime compose H. D prime compose R0 is D prime. What does D prime compose H? D prime composed with H is R90. Hey, that's the same set as the other one right above it. These are the same. That's no accident. And the notation suggests it should be true. If we're going to describe this notation with this terminology, this is the left coset of K and G containing R90. And yeah, it contains R90. And this is the left coset of K and G containing D prime. And yeah, it contains D prime. Different A's in front of the subgroup could give you the same coset, the same left coset. Real quick in 15 seconds, what's a right coset? It's ha. Hey, ah and ha. Another joke, just full of it today. It's the set of all elements that can be written as ha, little h times a as little h ranges over capital H. That's called a right coset. It's a right coset of H in G containing A. And it does contain A because I can replace little h by E. A is E times A, and E is an H if H is a subgroup. So the terminology makes sense. It does contain A. That's a right coset where the A is in the right. This is a left coset where the A is in the left. You might wonder, are left cosets and right cosets equal to each other? Well, certainly they would be equal if the group is abelian. And they are sometimes, maybe even you might say often equal, even if the group is non-abelian, it turns out, but not always. And that distinguishing factor about when left cosets and right cosets are the same is much more important than you might imagine. All right, have a good day.